Hello everybody, welcome to today's lecture for April 27th. This is going to be our second to last lecture where we talk about new topics. And the book discusses this in words and doesn't prove anything formally, so I took the liberty of writing up some proofs myself. So we're going to be talking about the last topic in chapter 5, which is factors, simple groups, and classifications of simple groups. So let's discuss what exactly that looks like. So the goal is to classify all of the groups of finite order. And as you saw, even just going up to 8, the arguments became very nuanced and complicated and very specialized to the specific order that we were looking at. So we want to find some sort of more systematic approach to describe what group structures look like. And to do that, we want to understand the relationship between one group and all the groups that sit around it. So rather than just try to understand all of the groups of order, say, 64, I want to think about how the groups of order 64 are related to the groups that have smaller order than it. And we already know that the divisibility properties of a number play a crucial role in determining what groups can appear. Because if the group has prime order, then it has to be cyclic. The cyclic group is the only one around. And as we'll soon see, more divisible numbers can have more complicated structures because there's more opportunities for those groups to have factors. So what's the idea? Well, we want to define what a factor is. So we already talked a little bit about group homomorphisms. And a homomorphism is called an epimorphism if it's surjective. So G is onto H. So in particular, the order of G has to be more than the order of H by the pigeonhole principle. And in this case, H is called a factor of G. So the images of G under epimorphisms, under homomorphisms, are called factors of G. So let's give some examples of epimorphisms and factors. All right, I can take Z4 and map it onto Z2 just by taking an element of 4, a congruence class modulo 4, and instead considering it modulo 2. And since the even numbers are contained in the multiples of 4, this is a well-defined map, and it respects addition. So it is a homomorphism, and it's obviously surjective, right? What's the map? I mean, we can write it like this: 0 goes to 0, 1 goes to 1, 2 goes to 0, 3 goes to 1. These are the congruence classes in Z4. These are the congruence classes in Z2. There's another order 4 group that has Z2 as a factor. It's the direct product of Z2 cross Z2. And in this case, I just project onto the first factor. So 0, 0 gets mapped to 0, 0, 1 gets mapped to 0, 1, 1 gets mapped to 1, and 1, 0 gets mapped to 1. I just look at the first coordinate. And indeed, this is a homomorphism, right? Because how is the multiplication defined here? Well, I just do the group operation here and do the group operation here, respectively. So if I multiply x1, y1 times x2, y2, this is x1 plus x2. I use the group operation on Z2, which is plus. And indeed, if I applied f to each of these elements individually, it's the same as, and then add them. I applied the group operation here, which is addition. It's the same as just applying it to this one. So that's the homomorphism property, right? A homomorphism property is that f of G1, G2 is f of G1 times f of G2. And here, remember, juxtaposition of group elements just means I use the group operation. Let's continue. the plus or minus 1 group with multiplication is a factor of Sn. And the map is just sign. Right? We proved that the sign satisfies this property. The sign of the product of two permutations is the product of the signs. And so F is indeed a homomorphism. And it's surjective, unless n equals 1. If n equals 2, then this is surjective. So what's the plan? The plan is to try to figure out how to define the multiplication on G by understanding its factors, right? I know how, when I multiply two elements, if I know what their sign is, I know what the sign of the resulting product is. So I basically just need to figure out how the multiplication on the rest of the group works, the even permutations. And if I understand how the multiplication on AN works, and I understand this factor map and the multiplication on this easier, simpler group, which only has two elements, then I can reconstruct the multiplication of the entire group. Is the moral. It's a bit more complicated than that in general, but that's sort of the strategy here. We're not going to be able to talk about the full classification and how to use this in the full classification, but this is one of the crucial ideas moving forward in the classification program. Okay, so what's the idea? The idea is now I want to try to classify groups that have no factors, right? If it has a factor, I classify the factor first and then try to build the multiplication on G by understanding the factor and the kernel, and we'll talk about kernels soon. You did on your homework a little bit already, but let's see what I mean by this. So a group is called simple if every epimorphism, which means that it's a homomorphism, as we just defined, it's a homomorphism that's surjective. If every epimorphism is either an isomorphism, so it's injective as well, the group, the factor H that you're mapping onto is just another copy of G, right? It's a bijection, so I'm not actually collapsing, I'm not simplifying the classification problem, and I'm not simplifying the problem of trying to construct the multiplication on G by looking at H instead. So either an isomorphism or it's the constant map, right? So if I factor onto just the trivial group, just the group with only one element, which is the identity, I don't really get anything, right? I don't get any bonus information about G because, well, there's nothing to be learned from the multiplication here. So simple groups are one where the only factors are isomorphic to the original group themselves and the trivial group. And as I said, this homomorphism, it always exists just by sending every group element to the identity map. This homomorphism we'll call the trivial homomorphism. And this is exactly what I just explained. G can't be related to a smaller group that's non-trivial. The only group G can be related to is itself and the trivial group. So what are some examples of simple groups? Well, we have the group ZP, where P is prime. Right? We know from Lagrange's theorem that every subgroup of this group will have to have either order 1 or order P, because P is prime. It has to divide P. If it has order 1, then it's trivial, and if it has order P, then it's everything. So this proves that there are only two subgroups. And how do we get factors from this? Well, we'll soon see it, but basically, if I look at the order of the factor, the order of the factor will also have to divide the order of G, which in this case is P. Or alternatively, from your homework, you proved that the set of things that map to the identity in your factor group has to be a subgroup. So either it has to be everything, in which case the things that map to the identity is everything, and the homomorphism is the trivial homomorphism, or it has to just be the identity, in which case the group is an isomorphism because it will be injective, or the map is an isomorphism, it will be injective. Okay, so this is our first example of a simple group. So here's an example of a group that's not simple. If G and H both are not the trivial group, then I can look at their direct product. And their direct product will not be simple because G will be a factor. If you remember from our first page, we had this homomorphism which just assigned to an element of the direct product the first coordinate coming from the first group. And this map, this assignment to the first coordinate, is always a homomorphism, and it's always surjective. So G cross H will have a factor, and it can't be isomorphic to G because I'm losing all of the data from H. So it has smaller order, and it's not the trivial group. So this group will have a factor. Sn is not simple. Why is Sn not simple? Because we always have the sign homomorphism. And really I need if n is at least 3. Because if n is equal to 2, then the sign homomorphism is an isomorphism. So S2 is just the identity permutation and the one that swaps 1, 2. So this is actually isomorphic to Z2. It's one of these examples. S2 is Z2. Okay. We also looked recently at this dihedral group, Dn, which is not simple. And if you remember, it was a group that had a bunch of rotations and reflections. And one of the things you can show, and I leave this as an exercise to you, is that if you define a map from Dn to 1 and minus 1, where all the rotations are taken to 1, and all the reflections are taken to minus 1, then this map is a homomorphism. The composition of two rotations is again a rotation, and the composition of any two reflections has to be a rotation. And finally, the composition of a rotation and a reflection is a reflection. So that will prove the homomorphism property. So that's Dn. Okay, and let's move on to the last one, which is simple. An, which is this kernel of the homomorphism from Sn, right? It's a set of all even permutations, does turn out to be simple if n is big enough. So it's not simple if n is 2, 3, or 4. If n is 2, then it's the trivial group. If n is 3, then it's a cyclic group of order 3. And if n is 4, then it's the group Z2 cross Z2. You can check this, I think. Or at least contains it as a normal subgroup. And we'll talk about what normal means soon. And how it's related to simple. But if n is at least 5, then this group is simple. And just as an application, again, it's beyond the scope of what we're going to do here. One of the earliest reasons for developing group theory was to analyze these permutation groups and in particular analyze how they relate to polynomials. And you can use this simplicity to prove that there does not exist a quintic formula. So what do I mean by this? Well, I mean, we have what's called the quadratic formula, right? Everybody learns this very easily, and this one is quite simple to understand and memorize. We teach it even to middle schoolers. But there's also formulas for third-degree polynomials and fourth-degree polynomials. They're much more complicated, and it's actually a bit of an algorithm for the fourth-degree one. It's not quite so simple, but these formulas exist. There's a procedure in place that if you give me the coefficients of a fourth degree or third degree polynomial, I can find all the solutions of that polynomial using an explicit equation. And what Galois proved is that the reason for the way that you can arrive at these formulas is by looking at the action of Sn by permuting the coordinates. And what's the point? The point is that Sn is built from abelian groups for n equals 2, n equals 3, and n equals 4, right? For n equals 2, it starts as abelian. For n equals 3, it has a factor which is abelian, the plus or minus 1 group, and then it has the cyclic group of order 3, which is also abelian. So it's you have a factor, and then the kernel of the factor is abelian. And part of the reason the quartic formula is so hard is because you have to do it 3 times. You have the abelian factor, then you have the kernel there, which has its own abelian factor, and then you have the kernel there, which is abelian. The quintic formula doesn't work because this is simple and not abelian already. So just as an advertisement for why you might care about these topics, once you know that the group is simple, you know there's a proof, and I'm not going to go through it, but there is a proof that you cannot find a quintic formula. Okay, so these are examples of simple groups and not simple groups. So here's a little exercise for you, and I'll put it in this week's homework too. Show that an abelian group is simple if and only if G is isomorphic to ZP for P prime. This exercise is the start of the classification program for abelian groups, which is much easier than the full classification program for arbitrary groups. Okay, so now that we understand what a simple group is, let's introduce a new definition and introduce a theorem that's going to be our main theorem for the day of when a group is simple, a criterion. So here's our definition. We know that a subgroup H is normal if for every group element in G, conjugating a capital H by G, so multiplying on the left by G and the right by G inverse. All right, this is just the set of all elements which can be written as G, H, G inverse for some element of H, is just equal to H again. Right, so somehow this is saying that left and right cosets are the same. And it's not difficult to show that this is equivalent to GH equals HG. This is the condition. So left and right cosets of H are the same. So there's one immediate thing that you can prove, and that's that if G is an abelian group, any subgroup is automatically normal. Because I can just rearrange this product. G and H commute if it's abelian, so I can push H to this side and commute G over here, and then I get G times G inverse times H, which is just H, which certainly belongs to H. So this condition is automatically true if G is abelian and H is any subgroup. But if G is not abelian, not every subgroup will be normal, as we'll see soon. So here's the theorem that is really the practical way to check whether a group is normal or not. Simple, rather. So a simple group is one that has no non-trivial normal subgroups. So what I mean by non-trivial? Well, there's one subgroup that's always normal. Actually, there are two subgroups that are always normal. One is the full group G, right? If I put G here, then G, H, G inverse has to be in G just by closure of group multiplication. Right? So if H is actually equal to G, then this condition is automatically true. So what's the other one that's automatically normal? Well, it's the trivial group, right? If H is the trivial group, then this set here is G times E times G inverse. So this identity element can be canceled out, and I just get G times G inverse, which is just the identity. So the only thing in this set is the identity, which is in fact equal to H. So these two groups are always normal. And the group is simple if these, in fact, are the only ones that are normal. So how do we want to prove the theorem? Well, we're going to prove it in many steps. So I'm going to put this theorem on hold and prove some intermediate theorems to get us to this one. So what's the first step of proving this theorem? Well, the assumption, simplicity is related to not having factors, right? So one of the things that you proved in the last homework was that if you have a homomorphism, the set of elements in G that map to the identity in H is a subgroup of G. And what we're going to show is that this is always a normal subgroup. All right, so we already know it's a subgroup from the homework. Now let's prove it's normal. So how do I prove that something is normal? What do I need to do? I need to show that this set is contained in here. And in fact, it's equivalent, but for simplicity, let's make this containment. So I need to prove that if G times H times, if I take any H in H, in this case K, if I take any K in K, and I conjugate it by an element of G, I stay inside of K. So I take an element of G, I take an element of K, and I want to prove that this element belongs to K. How do I prove that something belongs to K? I prove that when I apply F to it, I get the identity. So I apply F to this conjugation, and I want to show that I get the identity. Well, what do? I start using the homomorphism property to break up the multiplication, right? The homomorphism property tells me that because these two are multiplied, I can break off the G, and then I can break off the K. So I get that f of G, K, G inverse is f of G, f of K, f of G inverse. Then what do? Well, I use the facts that my assumption, right? My assumption here is that K belongs to K, which is the kernel. So the F, when I apply it to little k, gives me the identity on H. And now, of course, this can be canceled because it's the identity. And I get f of G times f of G inverse, which is the identity. Right? This is then going to be f of G times G inverse, which is the identity on H. One of the things you proved on the homework is that inverses are taken to inverses and the identity is taken to the identity. So that's this last step here. So that means that whatever this element is, it has to belong to K, because K is defined exactly as a set of things that map to the identity. So this belongs to K, once K belongs to K, and G belongs to G. And that's exactly what it means to be normal. That if I conjugate an element of K, H, I stay in H. So what does this theorem prove? This theorem proves that if you only have the identity group and G as the normal subgroups, then G is simple. Or in other words, if G is not simple, then I have a non-trivial normal subgroup. Exactly because I have a homomorphism, which is not trivial, right? If G is not simple, then it tells me there exists a homomorphism which is not trivial. And if that homomorphism is not trivial, then its kernel can't be everything. And it can't just be the identity element either, because it can't be an isomorphism, and it can't just be the trivial homomorphism. Okay, so we've proven half of this theorem, right? that if we have this condition, then G is simple. So now let's prove the other direction, that if we know that G is simple, then every normal subgroup has to be the identity or all of G. And for this, we're going to prove another theorem. And so what do I need to do? I need to assume that I have a normal subgroup and produce a factor just from a normal subgroup. And that's what we're going to do here. So what do I want to do? I want to fix a normal subgroup H in G, and I'm going to let L denote the left cosets of G, of H rather. Right? So L is going to be just the set of all cosets G times H. And this group L, which I call L because it's the left cosets, people usually denote it as G mod H. But for notational purposes, I'm just going to call it L. So what does this remind you of? It should remind you of the construction of modular arithmetic. When we talked about modular arithmetic in congruence classes, what did we do? Well, the congruence class mod 2, for instance, was that integer plus any multiple of 2. So the set of multiples of 2 is a subgroup. And so this is the set of cosets of the multiples of 2 is exactly Z2. So here we're doing the same thing, but in a more abstract group theoretic setup. I have a group G, a normal subgroup H, and I try to define a multiplication on these left cosets. So how do I do that? Well, I define the multiplication on L. What does it have to do? It has to take in two elements of L, which is G1H and G2H, two left cosets, and it has to output an element of L as well. So I just multiply these G1 and G2s, and I produce a coset this way. Now, already there's a slight problem, and that's that I don't know that this multiplication is well defined. Right? Writing G1H, G1 is not unique in this presentation, right? G1 was a representative of this coset. I could have picked a different element of the coset to represent it. So the first thing I need to do to prove that L is a group is to prove that this multiplication is well defined. Right, so if I picked different elements, G1 and G2, to represent these cosets, I would get the same output coset here. And then once we know the multiplication is well defined, we'll show it's a group. And actually, the harder proof here is proving well definedness. And this is exactly what fails when L is not normal. If L is not normal, this multiplication is not well defined, as we'll see soon. Because we'll need to use normality of H to prove that it's well defined. Okay, let's prove the theorem. So this is what I just explained. If we want to prove that this multiplication is well defined, I need to prove that if I chose different elements to represent these cosets, the output of this multiplication is the same. So let's go and prove that this works. So what do? I assume that I messed up and that I actually meant to choose A1 and A2 as representatives for these cosets, right? So suppose that if I chose a different element elements A1 and A2 in G, I got the same cosets of H. Now what do we want to do? We want to show that the output is the same. So the output, if I use the G1s, is G1 times G2 H. And the output, if I use the A1s, well, I just do the same multiplication definition, and I get A1 times A2 H. Now, what's the property of cosets that we proved that I'm using implicitly throughout this stuff? I know that cosets are either disjoint, so that they have no overlap whatsoever, or they coincide. So once I prove that there's something in the intersection of these two things, I know that the cosets are the same. So the only thing I have to do is prove that A1 times A2 belongs to G1, G2, H. Right? A1, A2 is an element of this coset because the H must contain the identity. So A1, A2 belongs to the right-hand side. So if I prove that it also belongs to the left-hand side, I will just show this inequality by the previous lemma we showed. So what do I want to do? Since for I equals 1 and 2, I have G1H equals A1H and G2H equals A2H. Again, because I can choose A1 on this side, I know that A1 belongs to G1 capital H. So I can find H1 such that G1 times H1 is equal to A1. And similarly, G2 times H2 is equal to A2. Now what do? I just want to substitute these two things in for A1 times A2. So I look at A1 times A2, and I see that it's equal to G1H1 times G2H2. Now let's again return to the abelian discussion. If G was abelian, then I could just move this H1 over to the other side, and I'd get G1, G2, H1, H2. And I'd see that A1, A2 belongs to G1, G2 times H, because H1 times H2 will belong to H. So I need to replace this argument in a non-abelian group with the assumption of normality of H. So I need to figure out how to switch the order of H1 and G2. Well, let's try to use normality with H1 and G2. So because capital H is normal, when I conjugate H1 by G2 like this, I still belong to capital H. All right, that's just what normality means. Normality means that when I do a conjugation of the an element of H by an element of G, I stay inside of H. Well, just give this element a name, H1 prime. So if notice that if G is abelian, then H1 prime is just equal to H1. But for now, we just have that H1 prime is some new element of H. Right? It's this, whatever element this is, I call it H1 prime. And if I solve this equation by bringing this G2 inverse, multiplying by G2 inverse on the left, I get G2 H1 prime is equal to H1 times G2. Well, now we're in very, very good shape, right? Because this exactly allows me to take H1 times G2 and write it as G2 times something in H. So if I start with this equation here, I've just copied this equation again. Here I isolate H1, G2. I just did this for emphasis, these parentheses. And then I substitute in G2, H1 prime into this parentheses. Well, regrouping, as necessary, I get G1 times G2 times H1 prime H2, and this has to belong to H. So what did I want to show? To show that A1, A2, H is equal to G1, G2, H. I already said that it suffices to show that A1, A2 belongs to this coset, and that's exactly what we did here. So all of this, the most difficult part of the proof, is to prove that this definition of multiplication on cosets is well defined. Okay, so now I have that this multiplication is well defined. I need to check that the group axioms for it. So there's 4 group axioms, and they're all quite easy to check. So what's the first group axiom? The first group axiom is closure. So by definition of the multiplication on L, the output of when I put in 2 cosets, I get a new coset. So the output of a multiplication is again an element of L, so the multiplication is closed. We're good there. How about associativity? Well, this is just going to follow from associativity on G, right? If I multiply two cosets first and then here, I multiply the elements of G, and then when I do these ones, I get ABC. Now, using associativity of G, instead of pulling out AB first, I can pull out BC first. So it's AH times BC. And then, again, just definition of the multiplication on L. This is BH times CH. So there's no associativity, just follows from the associativity of the multiplication on G. What else do I need to check? I need to check that there's an identity element. And there's an obvious candidate for this. It's just the identity coset, right? H itself is a coset of H. It's just identity times H. And this is going to be the identity element in L, right? Because by definition, if I take the identity times H times anything else on H, this thing is going to be the identity. So I'm just going to get this coset back. So the identity coset is the identity element of L, G mod H. And finally, again, there's an obvious candidate for inverses. It's the inverse of the coset GH in L is G inverse, where I take the inverse in G times H. And indeed, again, you can check very easily that if I put G1H times G2H, that's going to be equal to G1G inverse H, which is identity H, which is the identity element in this group L. So I've checked these four axioms. I've checked that the multiplication is well defined. So my set L is actually a group with this multiplication. So why did I care about constructing this group L? Well, once I have a normal subgroup, this L is going to be the factor. This is going to be the group that I can factor onto which is not the trivial group and not all of G. Right, so if H is a normal subgroup, there exists an epimorphism, so it's going to be surjective onto L, which just maps F. F takes F, G to L, and such that H is the kernel of L. So what does this mean? This means that we've already shown that if you give me a homomorphism, you can construct a normal subgroup, which is the kernel. This is the opposite construction. This shows you that if you have a normal subgroup, then you can construct a factor. So basically what this is telling you is that the isomorphism classes of factors are one-to-one correspondence with the set of normal subgroups of G. So classifying the normal subgroups is the same as classifying the factors. Or in other words, saying that a group has no factors is the same, no non-trivial factors is the same as saying that the group has no non-trivial normal subgroups. Once we carry this construction out. And the proof here, once we know that L exists and the multiplication is defined how it is very simple. How do we prove it? Well, we just proved that we can construct this group L, right? So we let L be this group as before, and I need to define a homomorphism, right? Well, it's very clear what the homomorphism should be, right? If you give me an element G in G, I can take its coset. So for any element G, I can construct a coset that contains it. So what do I need to show? I need to show that this map is surjective and a homomorphism to prove that it's an epimorphism. So first, let's check F as a homomorphism. What happens if I take F of G1, G2? Well, I just take the coset of this element, G1, G2 times H, which by definition is G1H times G2H. Right, this is how the multiplication on L is defined. But G1H is just F1G, and G2H is just F of G2. So what I've shown is that f of g1 times g2 is f of g1 times f of g2, and f is a homomorphism. Now, how to prove surjectivity? Well, any coset has a representative, right? Any coset has to be written as g times something. So if you give me a coset, I can certainly find an element of g that maps to it. You just choose some element of the coset, and that element will map to that coset. So f is definitely surjective. Now what's the last thing I need to prove? I need to prove that h here is the kernel of f. All right, so if, what is the kernel of f, right? It's the set of all of things that map to the identity in the target group. And here the target group is L. So if f of g is the identity on L, which is the identity coset of h, then, well, by definition of f, g times h is equal to h. But once I have g times h is equal to h, it's very, very easy to prove that g has to be an element of h, right? Because if g times h is equal to h, the identity is here, so g times the identity has to be in h. So once g times h is equal to h, g belongs to h, and what does that show? That means that the kernel is contained in h, right? If I have something in the kernel, then it has to belong to h. And it's also easy to prove that h has to belong to the kernel, right? If you give me any element of h, what is f of h? Well, it's little h times capital H, which is just capital H. So capital H is indeed the kernel of f. So it's these two theorems combined that really give the beautiful structure for factors and how they're related to normal subgroups. So if you have a factor map, the kernel is always a normal subgroup. And if you have a normal factor, a normal subgroup, you can construct a factor for which it's the normal, for which it's the kernel. So this could have been an alternate definition of a normal subgroup. Normal subgroups are the kernels of homomorphisms. Okay. And this is just one last remark. We've proven the main theorem that we wanted to prove. That if a group is simple, then it has no non-trivial normal subgroups. Because once you had a non-trivial normal subgroup, you could produce a non-trivial factor here. Right? This couldn't be onto the trivial subgroup because the normal subgroup, it wasn't all of G. And finally, this couldn't be an isomorphism because H is not trivial. So if H is trivial, then it's an isomorphism. And if H is not trivial, then it's not an isomorphism because it's not injective anymore. There's multiple things that map to the identity. Okay, so this is all for today. I know it's a lot to take in, but I wanted to do this properly. The discussion at the end of the book is very informal and doesn't really give a hint about the beautiful structure for simple groups and why we care about simple groups. So I hope you enjoyed the lecture. There'll be one more on Wednesday with new content, and then we will be wrapping up with a review lecture on Friday. I hope you all are staying safe and doing well, and I will talk to you soon. Bye-bye.